Hello everyone, and welcome to the speeding up and slowing down post-activity. So what I want to do here is to go over some parts of the speeding up and slowing down activity that you completed. Basically, I want to go over the summary page because it's kind of important. Right? And then I want to go over a little bit of numbers 5 and 6, in particular the graphs and especially the motion maps, which get a little complex. So, the summary page. After you did 1 through 4, hopefully you realized that positive and negative acceleration may not mean what you thought it meant. Most of you, I think, if I would have asked, what do you think it means to have a positive versus a negative acceleration, probably would have said, well, speeding up and slowing down, right, is what that means. But as you went through the examples, you saw that that might not be true, right? So there is, though, a pattern that we can use that will help us remember, or interpret, I should say, a positive or negative acceleration, and it'll tell us whether we're speeding up or slowing down. So the key is to compare that acceleration to the direction the object is moving, which you can see on either the displacement or the velocity of it, right? So if we go back and look at the first 4 here, okay, just 1 through 4, in number 1, were the velocities positive or negative? Right? They were positive. The accelerations were positive, and your walking man was speeding up. Right? If this doesn't ring a bell, go back and look at the activity, right? In number 2, he was walking in the positive direction. He was walking to the right again, right? But this time he had a negative acceleration, and he was slowing down. Now at this point, most of you are probably rolling right along going, yeah, makes perfect sense. Positive acceleration speeding up, negative acceleration slowing down. And then you get to number 3. This case, he went and walked to the left, so he had a negative velocity. Right? He started way out at 10 and walked back to 0. His acceleration was also negative in number 3, and he was, speeding up. So here we have number 2 with a negative acceleration and slowing down. And in number 3, we had a negative acceleration and he was speeding up. Then to make matters worse, in number 4, he was also moving to the left, so he had a negative velocity. His acceleration was positive, and he was slowing down. So in number 1, a positive acceleration speeding up, and number 4, a positive acceleration slowing down. So obviously, it's not as simple as just going, oh, positive is one thing and negative is the other for an acceleration. It's more complex. But do you see a pattern when you compare the sign of the acceleration to the direction the guy was moving? What do you notice? What does it take for him to be speeding up? Yeah, right? The direction he's moving and the acceleration have to be the same direction. Both positives, number 1, both negatives, number 3, both speeding up. And if they're opposites, numbers 2 and 4, then he's slowing down. There's the pattern. You can't just look at an acceleration and know what that means about the velocity. Oh, it'll tell you how quickly the velocity is changing, but it won't tell you whether it's speeding up or slowing down unless you also know the direction it's moving. Now, there's 2 good reasons for this. One I'm going to leave for next unit. The first reason for this is really a math reason. I don't want to get too deep into this, but remember that acceleration is the rate of change of velocity, which is itself the rate of change of position. Right? And that throws a couple of places where you can get negatives. One, since acceleration is change in velocity over change in time, right, you can get negatives because your velocities are negative, because you're moving to the left. But you can also get a negative thrown in your change in velocity. If your final is smaller than your initial, right, you get a negative. And because there's a couple of negatives that can be thrown in, a vector one and an algebraic one, it's not, acceleration just is not as simple as it seems, as we've been saying all along. It's a tricky little thing, but this is the pattern, right? So I'm hoping you remember this pattern. And if you were good about drawing your motion maps, I really think that motion maps are probably the best way to lock this into your brain. After you draw a few good motion maps, all right, you really should see this pattern. To help lock it in, let's talk a little bit about 5 and 6. So 5 and 6 was slowing down to a stop while moving in the positive direction and then speeding up while moving in the negative direction. So this was him going from 0 out to about 9 and then from 9 back to 0 again. Right? It had a position of 0, a velocity of 6, positive 6, so he's going to start out moving to the right, and an acceleration of negative 2. And of course, you saw something happen like this. Watch the graphs. Gets all the way out to the far right, and now turns around and comes back. He's going to stop when he gets back to 0. Boom. Now look at the graphs, right? For the first time, we didn't just get the half parabola. We got a full-on parabola here. It's upside down. It's bottom opening, I guess you could call it, but it's still a parabola. We got a single diagonal line, but for the first time, it crossed the time axis. That means it changed direction. Right? Above the time axis is positive velocities. This was when he was moving to the right. Right? And below the time axis are negative velocities. This is when he was coming to the left. But the entire time, the acceleration was negative 2. That's kind of interesting, isn't it? That the acceleration was uniform, even though the motion was completely different kind of motion, right? Speeding up in the positive direction, slowing down in the negative. Huh. And on my page that I had you fill out, right, on your activity sheet, I drew a dotted line down the middle, which is where I wanted you to put basically the rightmost point, right? So this is his rightmost point when he got to about 9, because I wanted you to look and notice that at that rightmost point, his velocity was 0, but his acceleration was still negative 2. It wasn't 0. See all that? So your graphs that you hopefully sketched look something like this, right? Okay. Now, let's draw the motion map. Okay. He starts out at position 0. He's going very fast to start out with. Well, relatively fast, 6 meters per second. So the dots are going to be far apart, but then he's slowing down, so the dots are going to get closer and closer. Now, this next dot is going to be the dot that's represents a position that's the highest on the position time graph, which is the rightmost point, right? When he was all the way out at about 9 meters, I think, in real life, or in the simulation. Now, I could put that about here, except the problem is, what's he do after the dotted line? Well, he comes back to the left, and I don't want to overlap because, you know, it'll be a big jumble, be hard to interpret. So I'm going to take this point and jump it up a level. Now, you might be saying, but wait a minute, there's not a point down here. Well, no, there isn't. Because think about what that meant when we first learned these motion maps. If we had a dot here and a dot here, 2 dots that were right above one another, right? What does that mean? Well, that means that he stood still for a unit of time. The walking man doesn't stand still for any amount of time. He doesn't get to 0 velocity and then flatten off for a while and then start moving back. He moves smoothly through 0, turns around, and comes right back. Okay, so when you have a thing like this, right, this is when you're instantly turning around, right, and changing direction. You don't stop for a while and then go in a direction. That's why we get this little jump here, okay? Now, on his way back, he's going to speed up. Notice the slopes here get steeper. The velocity gets further away from the time axis, right, further away. And so the dots are going to start out close and get further and further and further. Now you might be saying, wait a minute, you put those somewhere. Yeah, just, you know, if you want to adjust your diagram, go ahead. Make it look like mine. I'll explain in a moment. So here's the dots. Velocity arrows, well, they start out big, and then they get smaller and smaller and smaller because it's getting slower and slower and slower. At the rightmost point, what's the velocity? 0. This is where he's changing direction. So there is no velocity arrow there. Here, the velocity arrow will be pointing to the left, right? And then to the left bigger, and to the left even longer, and to the left even longer, because he's going faster and faster and faster to the left. Now you might say to yourself, wait a minute, how come you didn't fill this space in? It wasn't a mistake. There's a reason for it. I'll explain again in a minute. All right, just hang on. If you're looking at yours on your page and yours doesn't look like mine, you may want to fix it, okay? Let's do the acceleration arrows, and then I'll explain kind of a couple of the real nuances to this process. So first off, look at his acceleration. It's negative all the time, which means the acceleration arrows are always going to point to the left. Also, it's a constant acceleration, so the acceleration arrows are going to be the same size. Notice, here he's moving to the right, the acceleration points to the left, and what's he doing? He's slowing down, right, when they point in opposite directions. To me, when I first saw motion maps, and this was, a decade after I had learned physics in college, right, and I went to something and saw these, I thought, that is just a beautiful way to show this kind of pattern that they have to point in opposite directions. Because to me, it just kind of made sense that when you put the acceleration arrow pointing the other way, the velocity was getting smaller by this amount. Right? The velocity arrow was getting smaller by that amount. It was taking away from the velocity. And it wasn't helping, it was working against it. But on the way back, the acceleration arrows point in the same direction as he's moving, and so he's speeding up. See how he can have the same acceleration, but have two kinds of motion? It's all about what direction he's moving. And yeah, there is an acceleration arrow on the rightmost dot, because if there wasn't, he wouldn't come back. Right? He'd get stuck there. And he didn't get stuck there. Right? When you push a cart up a hill, it doesn't get stuck at the top. It comes right back down. Right? So there's just the one point where it's instantaneously a velocity of 0. So let me go through the nuances here, right? When he's walking to the right, the dots get closer together and the velocity arrows get shorter because, and the acceleration arrows point in the opposite direction to the motion because it's slowing down. At the furthest point to the right, the instantaneous velocity is 0 because he's changing direction, but he is still accelerating because he's changing direction. Something's still happening, right? And think of the counter. If it was 0 and he had no velocity, he would never come back. Right? He'd get stuck there. He doesn't get stuck there. And then on the way back to the left, the dots get further apart while the velocity arrows get longer, and the acceleration points in the same direction because it's speeding up. Got all that? I mean, there's a ton that you can see if you draw this properly that you must understand in order to draw it properly. Right? If you're thinking about what you're drawing. Velocity arrows, position dots, acceleration arrows. Now, a couple of things about what I drew, right? And why I drew it the way I did. Did you see the symmetry? Look here at your position graph, right? It was a nice parabola. Look at your velocity graph. Yeah, it's opposite, but it's the same slope, right? And your acceleration. There's some beautiful symmetry here, and symmetry is your friend in physics. It shows up in a couple of places, right? Because the acceleration is constant, that means that he is slowing down just as quickly as he speeds up on the way back. With me? On the way back, he speeds up just as quickly as he slows down on the way there. That means that your dots on the way back should be at the exact same positions as your dots were on the way out. Everything is nice and symmetric. So you can draw a vertical line through these dots in each case. And that's also why I drew the velocity arrows that way. How fast is he going here compared to here if he's accelerating the same? Well, if this is like the dry ice puck, right, that's 0.1 seconds later, and then, or if this is the moving man and it's like a second, right? This is a second the other way. He's got to be going the same speed, right? So these two arrows are the same. And these two arrows have to be the same length. And these two arrows have to be the same length. And these two arrows are the same length. Right? At the same position, he's going the other direction, but the same speed because everything is nice and symmetric. That's why we get that perfect parabola. That's why we study uniformly accelerated motion. And we can do it without calculus. Anything more complex than this, we really need the calculus. Right? So, two things here. The corresponding position dots are in the same position. See those? Right? Those are in the same position on the way out as the way back. And the velocity arrows of corresponding positions are the same. Those two are the same length. Those two are the same length. Right? Those are the same length, and those are the same length. So I would highly suggest you go back and fix your motion map. If you need to pause your, this video, go ahead and pause it and get the motion map drawn correctly on your activity sheet. Okay? All right, so I want to do the same thing here with number 6, except I'm going to go a lot quicker because it's really the same, just pointing in the opposite direction. So here he's going to start at position 10, so he's starting way out here. He's moving to the left at 6 meters per second to start out, and he has a positive 2 meter per second squared acceleration, and let's watch the motion. So he's slowing down, moving in the negative direction. Flips around and goes back. Notice he didn't stop there, and speeds up on his way back. Basically the opposite graphs, right? You get the top opening full parabola. You get the upward sloping diagonal line, again going through 0 because it's changing direction. Here he's slowing down, here he's speeding up, and then a constant positive acceleration, right? So hopefully your graphs look like that. Motion map, well, this time he's starting way out here, going to the left, going fast, so the dots are far apart, they get closer and closer. There's the highest point where he's going to, the lowest point on the graph, which is the leftmost point in real life, in which he's going to flip and go the other direction. Right? On the way back, we get that symmetry, and he speeds back up just as fast as he was slowing down. Velocity arrows, fast, slower, slower, slower. No velocity arrow, because at the leftmost point, his velocity is instantaneously 0, right? But then he starts to accelerate positively and speeds up, but symmetry again, right? This arrow, same size as that arrow. This arrow, same size as that arrow. He is speeding up just as quickly as he slowed down, right? So equal positions have equal speeds, opposite velocities. Acceleration is a constant positive acceleration, so it's always going to point to the right. Notice that as he moves to the left, if the acceleration points to the right, what's he doing? Slowing down. On the way back, the acceleration points to the right, and he's moving to the right, so what's he doing? Speeding up. Again, it kind of makes sense, I hope. When they're pointing in opposite directions, the acceleration is taking away from the velocity, it's slowing him down. When they're pointing in the same direction, it's adding to the velocity and he's speeding up. This is the pattern that we found. So if you can do these two motion maps, that's pretty much as complex as the motion map gets in this unit. But there's a tremendous amount of information here, right? And there's a tremendous amount of information in the graphs as well. Right? But remember that none of these are actual reality. They are all just representations of reality. But if you know the rules of the representation, if you know the language, right, the language of graphing, the language of motion maps, eventually in this unit, the language of mathematics when we get to math models, equations, right, then you can read what's going to happen and make predictions about uniformly accelerated motion.